Hello everyone. In this video, we'll look at how real-world assets can be bought on-chain using smart contracts and how RWAs turn real value into digital tokens. Before we proceed into that, let's first understand what Rootstock is. So Rootstock is a smart contract platform secured by Bitcoin that brings Ethereum-compatible smart contracts to the Bitcoin ecosystem. It allows developers to build decentralized applications using Solidity while benefiting the Bitcoin's security. The key features of Rootstock are like the Bitcoin level security. Rootstock is secured through merged mining with Bitcoin inheriting the Bitcoin hash power. This makes it one of the most secure smart contract networks available. Rootstock is also EVM compatible, that it's fully compatible with their Ethereum virtual machine, that's EVM. So developers can deploy their Ethereum smart contract without rewriting their code. It's also a smart Bitcoin, that's RBTC. So Rootstock uses RBTC, that's 1:1 like with Bitcoin as a native gas token. BTC can be locked on Bitcoin and used as RBTC on Rootstock for transactions. Rootstock also gives a lower transaction fees compared to Ethereum mainnet. Rootstock offers significantly lower gas fees. This makes it quite suitable for a real world and enterprise grade applications. Also, the transaction that happens on Rootstocks are quite faster. Rootstock has faster block time than Bitcoin, enabling it as a quicker transaction. Confirmations, that's ideal for DeFi payments and tokenized assets. So now let's understand what's RWA. So RWs are the real world assets that represents physical or traditional financial assets like real estate, bonds, commodities, or invoices tokenized as digital tokens on blockchains to bridge traditional finance with DeFi. So this tokenization unlocks liquidity for illiquid assets by enabling fractional ownership, 7 trading, and automated yields via smart contracts. So in 2025, the RWAs have surged, overtaking DEXs as DeFi's fifth largest category, with about 24 billion plus dollars in non-stable coin value and driven by tokenized US registries and private credits. So now let's understand how RWA tokenization works. What are the process of tokenization? Tokenization of RWA will convert physical or financial assets into blockchain tokens, representing the fractional ownership, ensuring legal backing, and on-chain traceability. So first is the asset identification and valuation. So this is to identify suitable assets like property, treasuries, and appraise their values using independent auditors, document ownership via title deeds or financial statements. Then we have legal structuring. So it forms an SPV, LLC, or a trust to hold the asset legally, comply with regulations like SEC or MiCA through KYC. Then the next process is custody and off-chain setup. So it will transfer its asset to a regulated custodians, integrate the oracles for proof of reserves and real-time data feeds. Then we have smart contract deployment. So in this, it chooses blockchain like Ethereum or BNB chain, then code ERC20 or ERC1400 tokens with compliance logic for transfers, dividends, and redemption and audit contracts. Then we have token minting and issuance. So in this, the will mint a tokens 1:1 backed by smart contracts, and then will conduct STO or private sale with investors onboarding and whitelisting. Then we'll have the distribution listing that will distribute via platforms, list on complaints, DEXs, AMMs for secondary trading and automate deals. Then we have the ongoing management that will use oracles for updates, enable redemption, maintain audits, and governance. Now let's understand what are the key benefits. So the first key benefit is the liquidity, enhanced liquidity. So it fractionalized about $100 million real estate into 100 tokens for global access. Then there is transparency. So this immutable blockchain records reduces fraud. Oracles verify the reserves. The next benefit is this efficiency. It cut the intermediaries, enabling instant settlement. Then there's yield. So tokenized treasuries offer about 4 to 5% APY in DeFi pools. There are also some challenges in despite its potential benefits, tokenization also presents some challenges like regulatory consideration that differ by jurisdiction are significant concern to it. So now let's go and see the top 2025 protocols. So first is centrifuge protocol. So it focused on assets like invoices and receivables, and its key feature was the DeFi collateralization. It was among one of the top 10 RWA. Then we had Ondo Finance. So Ondo Finance was US treasuries, which mostly had a key feature of institutional yield, and it really had a high growth. Then we have Chainlink. So Chainlink is an oracle for all the RWAs. Key features are the data feeds and cross-chain. The another protocol was a realty. So this focused on assets like tokenized real estate, and it was for rental yield on Ethereum. It was a niche leader. So this complete was all about our. So now we'll go on seeing what all prerequisites are. So just click here Git. So Git is a distributed version control system that is used to manage and track code changes. So it allows a developer to collaborate efficiently and maintain its code history. Also, it can roll back to the previous versions when needed. So from this gitscm.com, you can install it in your so here it's for install for Windows. You can just click here and install this Git. Then next will require Foundry. So get Foundry. So Foundry is a fast and powerful Ethereum development toolkit that includes Forge for building and testing smart contracts and Cast for interacting with deployed contracts. So it supports a Solidity natively, and this provides advanced testing, scripting, and debugging features. So we have used Foundry this project to compile the contracts, run tests, deploy. So there are steps to download the Foundry. So you just go to this website, getfoundry.sh, and you just get this command on your terminal and download the Foundry. Then next is node.js. So node.js is one of the free open source cross-platform JavaScript runtime environment that lets developers declare servers and web apps, command line tools, and scripts. Here you can just go click here on get node.js, and you can just download node.js from here for Windows, or you can even do it for Mac OS, Linux, AIs accordingly. Then we'll go for seeing a wallet. So metamask.io. Go to this website because we'll require a wallet. Click on get MetaMask, and then it's redirecting me to the MetaMask because I've already installed it. But if you're new to it, you can just install it. Then go to chainlist.org. From here, you can search any network. I'll just include testnet and I'll search for Rootstock testnet. So you can just simply add it to MetaMask here, and you can just confirm because we are updating it to Rootstock testnet. You can do it for mainnet as well, or for any network that you want. You can add it to your wallet, whichever you have downloaded. Then we'll go for searching Rootstock faucet. and then here Rootstock faucet, and we'll just from MetaMask we'll put our public key. I'm taking my public key Rootstock testnet here and pasting it. Clicking I'm not the robot, and I'll get the RBTC. So this Rootstock RBTC faucet is to get free RBTCs, test RBTCs that are the testnet version of RBTCs. It's sent successfully to my address. So these are used for development and testing purposes. It is no real monetary value. It just we can deploy, test, and interact with smart contracts without spending the real funds. So this were the main prerequisites required. Also, we will see Rootstock RPC URL. So for mainnet, we have this URL as https public node rsk.co, and for testnet, we have this. So for mainnet, we have chain ID 30, for chain ID 31 for testnet. So we can have the RPC URL as well. That are the endpoints for deploying or interacting with the contract. So that's all the prerequisites we are required to know to build this project. Now let's go on building the project. Now let's go on building our project. So I've opened here a cursor, a code editor, and I've opened a folder here named as test underscore RWA. Now I'll open the terminal and I will just go on opening the git bash, and I'll give the first command as forge init. This forge init is the first command that we'll give. This is used to set up a new Foundry project, and it will automatically create a standard project structure with folders like src, test, script, and library. It will contain all of these. Now we'll go on installing forge std. So we'll give the command as forge install. So this is the command that was used to add forge std, which is Foundry's official standard library for testing. So it provides some essential tools like test-based contract, powerful VM cheat codes for manipulating blockchain state, assertion helpers, and debugging some utilities, making our smart contract testing quite fast, expressive. And another installation that we'll do is of OpenZeppelin contracts. So forge install OpenZeppelin / OpenZeppelin contract, OpenZeppelin contract, and we'll just run this. So this will install the widely trusted OpenZeppelin contracts library, which will contain the secure, audited, and reusable implementation of common standards such as ERC20, ERC721, access control, and also the security modules. This will allow the developers to build robust smart contracts without reinventing any core functionality. So this will just install this OpenZeppelin. Till the time, let's go on understanding what all these are. So here in this library, we can see the both libraries that we have installed right now, the Forge STD and the Zipline contract. So this includes our OpenZeppelin contract, which is a contract that is a battle-tested library of a secure smart contract that used across Ethereum and EVM chains. So it will have all of these. Then we have this Forge STD. Forge STD is the Foundry's official standard library that is used for testing, scripting, debugging the smart contracts. Next we have is script. So script is like contains all the deployment and automation scripts. So it will contain the Foundry scripts that is used to deploy the smart contract. We'll just delete this because we'll be writing our own script. Then SRC SRC contains the core Solidity smart contract that will define the business logic of the project. It is the heart of the application, like all rules, permission, and state changes live here and are executed on chain. So it contains the main protocol contracts, core logic for minting, transfers, and permission. We'll have two contracts here, rskdex.solid, mock ERC20. Then we have test. So this test folder will contain the automated unit and integration test written using Foundry. So smart contracts are immutable once deployed. So they must contain or must go through thoroughly tested before going live. This automated test helps us catch the bugs easily. Then we'll delete this test file as well. Then here we have git ignore. Git ignore tells Git which files and folders should not be tracked in the version control. So this exists because some files are generated automatically. They're environment specific, sensitive, or temporary. Then we have Git modules. So Git modules tracks Git submodules used by the project. So Foundry installs some dependencies like we have installed OpenZeppelin or ForgeSTD as the submodules. Then Foundry log. So Foundry log is the Foundry's dependency log file. It pins dependencies to exact commit hashes, ensuring a consistent build. So it just logs OpenZeppelin and forced STD's versions, preventing it from an unexpected breaking changes. Then we have a Foundry TOML. So Foundry configuration file defining a compiler version, optimizer settings, RPC endpoints, and project behavior. It is the main configuration file for Foundry. It defines how your smart contracts are compiled, tested, and deployed. Instead of passing options every time in the terminal, this file centralizes all project-wide settings in one single place. Then we have readme.md. So this provides a high-level overview of the project, its purposes, the features, setup instructions, and usage guide. This is the main documentation file of the project. It gives readers a high-level understanding of what a project does and how to work with it. It acts as the entry point for anyone visiting the repository, the developers, reviewers, or the contributors. So that's all about we have here. Now we'll go on writing our contract. So in SRC, we'll create one new file and we'll name it as AllowListRegistry. So in this file, we'll be writing all our contracts. So this allows registry. It is actually responsible for managing which addresses are permitted to interact with the RWA token. This will be using OpenZeppelin access control. So that's only authorized roles can add or remove the users. Also, this contract will help enforce the regulatory compliance. So now let's just go on writing the contract. First, we'll give SPDX license. So this is just a license identifier for the contract as it's required by the Solidity compiler. Now we'll give Dogma Solidity 26. So we can just take any version about this or below 0.9.0. Now we'll be importing. So we'll give import access control and we'll just go and importing this from OpenZeppelin, open the line back. I'll just write the address of it, where exactly it's located on the access control dot show. So we are just importing this. So this imports OpenZeppelin access control contract. It just provides the role-based access control mechanism. Now let's give a contract. So let's in the contract AllowListRegistry is an access control. So this will declare the contract and inherit from access control for the role-based permission. Now we'll give inside this, we'll give bytes 32 public constant, public constant, and name it as register underscore role, and this will be equal to check 256, and as we've named it as a register role. So this will simply define role for this register role, and the kick at 256 hashes the string into a bytes 32. Now we'll be doing mapping. So mapping address to boolean and very this private and this is verified. So this keeps the track of whether an address is verified, allow listed or not. And similarly, we'll do mapping again from address to bool, but now here we'll be doing it for Rosen. So is Rosen. So this will keep the track of whether an address is frozen or it's frozen in the sense it cannot interact with the token or not. We'll just see how's the interaction. Now we'll give event as verified set. In this we'll give address indexed account. The bool is verified. Yeah, the won't be underscore. So this will just event emitted. It will just emit the events like the verified status is being set. Then similarly, we'll have event for frozen set address index account bool is. Now we'll go on using a constructor, and in this way I will give address admin. Once the constructor is run, then the contract is deployed. Now we'll give require not equal to address 0. So here this will ensure that the admin address is not 0, which is if it is 0 then it would be invalid. So here we have mentioned the not equal to. Then grant role, which would be a default admin role. Default admin role. Here we have assigned the default admin role to the specified admin. Now we'll just again grant another role. That's a register role, and this also to the admin. So we have granted two roles like default admin role and register role to the same admin. Now we'll give another function as is verified address account, and now here we'll give the external view returns bool. So now in this we'll give return is verified and the account. So this is a public function to check if an address is verified or not. Now after this we'll give another function as address account. Similarly we'll be giving all of it external view return and the bool. Inside this we'll get the return function and the account. So similarly, this is to check if the address is frozen or the next function that will be defining or declaring is set verified. Set verified address account bool will and the external again will give an external only role and will give our register. So this will allow the addresses with registered role to set verified status of a single address. Now I'll give is verified that will be equal to verified. So this will now update the mapping with the new verified status. And we'll give emit verified set account verified. So this will emit an event to log the action on chain. Now next function that will give us set frozen. Function set frozen. Similarly, here we'll be adding similarly external only role will add as register role. So here up we have seen about verification. Now here it will allow the addresses with this role to freeze or unfreeze accordingly from a single account. Now we'll give this frozen account as frozen and now we'll emit our frozen set. We'll just emit the event for the transparency. That's it. Now we'll create another function as batch set verified function. I will leave it as batch set verified address. Then we'll have the call data accounts rules. Again, the call data values. And then we'll give our external. And inside that we'll write only the register. Now we'll just in the function in this now we'll write require accounts dot length that will be checking is equal to values dot length, and if it does happen, if it is verified, then it will just print length mismatch. So this is just to ensure that the arrays are of the same length to just avoid the errors. Or up we have just did the batch updating, so it will just allow the batch updating of verified status for multiple accounts just at once. So here it will now check if the lens are seen or not, just to avoid the errors. Nothing. Then we'll give a for loop. Inside that we'll write uint 256 I, that's equal to 0, and we'll give the condition that I less than accounts dot length, and we'll just do the increment I plus plus. Now we'll give is verified the accounts, and this would be equal to values. So this updates each account with its corresponding value, and I will go on emitting. So emit verified set. So this will emit an event for each change values. Now we'll create another function as batch set frozen. So similarly, as we created here for the batch set verified, we'll be creating these things. Just should be replacing the verified with frozen. Let's just go on copy pasting this and do the minor changes. So here, either than batch set verified, we'll have batch set frozen. This all will be fine. Then here, we'll have the changes here is verified will be replaced with is frozen, and here the verified set will be replaced by frozen set. That's it. So here again we have seen that this will ensure that arrays having same length to avoid this index errors. Then this will update each account's frozen status, and this will emit the event for each update that happens. That's it. So this was all about our AllowListRegistry sold contract. So in this overall contract, we can see this have managed the compliance layer for the Aditii system. So it maintains two key status for each address. The first is the verification and the frozen status, which we have seen throughout the contract. So verified addresses are allowed to interact with the RWA token, while the frozen addresses are temporarily blocked from transfers or other token operations. The contract uses a rule-based access control where only accounts with the registrar role can update verification of process statuses. Now we'll be creating one more contract. For that, in SRC, let's create one more file and name it as RW. So we're creating this contract because this will extend the OpenZeppelin standards to create a compliant ERC20 token. So this will ensure that only verified users can hold or transfer the token. Admin can pause the system if required. The token aligns with the real world regulatory expectations. So now let's go on building it. Identifier, give a Pragma Solidity version. Let's give it 0.8.26. Now we'll go on importing. So import ERC from OpenZeppelin contracts, OpenZeppelin contracts. Then again we'll import another one. So this one will import standard ERC20 token implementation from OpenZeppelin. Now we'll be importing ERC20 permit. So ERC20 permit, and we'll be importing this from OpenZeppelin contracts token ERC20, the extensions and ERC20 permit. So this will import ERC20 permit for a gasless approvals feature. Then importing the possible. So import possible. So we'll be importing possible from OpenZeppelin contracts slash the contracts security possible dot. So this will import possible contract to allow the emergency pause and pause of the token transfers. Now we'll be importing the access control as we did in the last contract as well. So import access control from bands. All have been taken from OpenZeppelin contracts only. Um, access control. So now all our imports are done. I'll go on creating an interface. So interface, I will give an interface named as I allowlist. So this will interface to interact with the allowlist registry. And this will be giving a function is verified address account name view returns the bool. So this function will check if an account is allowlisted or it's verified. Similarly, we'll be creating the same for is frozen. Also, it will be returns. So this will check if an account is frozen, that is, it cannot interact. Now let's give contract. So let's create a contract and name it as RWA token, that is ERC20, ERC20 permit, possible, and access control. So it will inherit it C20, ERC20 permit, possible, and access control for all its functionality. Okay, so now let's go on defining role for permission management. So bytes 32, public constant, and first we'll get pauser role, that would be equal to bracket 256 in the pauser role. Similarly, we'll be creating a mentor role, burner role, compliance role. Just changing the name here. Instead of pauser role, we'll give mentor role. Here, third, we'll be creating a burner role. The last role that we'll be defining here is compliance role. So that's all four roles that we have defined here for the permission management. Now AllowListRegistry public. So now we'll give AllowListRegistry. That will be a public registry. It's a reference to the AllowListRegistry contract for the compliance checks. Now we'll give all the errors, just custom errors for the better gas efficiency and the clarity. First one that will be given is error not verified, error is not verified. We'll have the address not found. Then we'll give an error as frozen, address found, and then we'll give another custom error as zero address. That's an invalid address if it's been entered. There's three custom errors that we have mentioned just to have the better cache efficiency and clarity for the users as well. Now we'll go on creating events. So let's give first event and we'll name it as registry updated. Registry updated. So here we are just giving this events for logging some important actions. As first action is if we are just updating any registry, so that's for that. And second is if there's a post transfer occurred. That's the another action that if it's taken. Address index ROM and then we have UN token and the address indexed operator. So this two event we have given. Now we'll give a constructor. Inside constructor, we'll just give the names what we want. First in string memory, we'll give name. Then similar we want the symbol to be displayed. Then address of the admin, also the address of the registry. So now here we'll give our ERC20 inside the name, comma the symbol, and then ERC20 name. This will initialize the ERC20 and ERC20 permit with a token name and the symbol respectively. Equal to, so it will check if the admin address is 0 or not. Also will give a gate and the registry, and it will check the registry address and then it will revert it 0 address. So this will just prevent 0 addresses for admin or registry. It won't give any invalid address as an error. Now I'll grant the roles to the admin as we did in the last contract as well in AllowListRegistry.sol. Similarly, here we'll be granting some roles. The default admin role will be given to admin. Then we'll be granting all the roles to the admin itself. All the roles that we have defined till yet. What all were there? First was default admin role. The second that we defined was our pauser role. Then we had minter role. Then we had burner role and companions role. So we have just granted all the roles that were present to the one admin itself. Now we'll give registry equal AllowListRegistry. So this will set the AllowListRegistry reference as a reference. We'll just emit the registry updated. Just log the registry initialization. So now we'll be creating another function as pause function. And we'll give the pauser role to it. Pauser role. And this one pause. The pause token transfer only callable by the pauser role that we have given, granted. Similarly, we'll give another function as unpause. This will unpause the token transfers. Now we'll give a function as registry. So here in this, We'll give address of a new registry. Then external and in only role here we'll be giving a default admin role. And we'll give if command, and in this if we'll give the condition as if the new registry is equal to an address, it will check if the address is not zero or not invalid, then it will revert the zero address. Then registry is equal to I allow list registry, and inside that will have the new registry. And finally we'll emit registry updated with the new registry. So here this is the updation of the AllowListRegistry, and this can be only called by the admin itself. Now let's go on minting the tokens. So we'll create another function as and we'll give address UN256 amount, and then here in this we'll give an external only role for minter, the role that we have given, minter role, and here we'll give enforce not frozen. So this enforce not frozen will check the frozen status. Then enforce verified is to check the allow list status, whether it's verified or not yet. Then we'll have mint to format the amount. So this one is called the OpenZeppelin ERC20. The complete motive of this function mint is to mint a token that has to be verified and the non-frozen address. And this will only be done by the minter role. Similarly, we'll be creating another function as born. So here, instead of 2, we'll be taking it, so it's from, and here it will be done by borner role. So here, wherever we have used 2, that would be replaced by from, as here born tokens from a verified and a non-frozen address. There we are minting the tokens to a verified, but here we are burning the tokens from a verified user address. And yes, this can only be done by a burner role. We'll create a function as force transfer function and name it as force transfer. Here we'll have the address from address to and the event of checks amount. And here the only role will give it to our compliance role. And inside this we'll give an if command and we'll check from is equal to address 0 and we'll give a can gate. Also check the condition as whose address is 0 valid or not. If both conditions are true, just revert a 0 address. Now we will give a super dot underscore update that would have from to and the account. From to and the account. So this will bypass compliance hooks by calling the parent update directly. Now finally we'll be emitting the forced transfer from to account to message.sender. Now another function that we'll be creating is function underscore update, in which we'll have address from and address to and the account amount, and we'll give this internally. So this is an override ERC20 update. So we'll give it internal and override then not. So simply it's an override ERC20 update to include the compliance check. Not, and we'll check the mint. That's from is equal to address 0, and then it will mint enforce not frozen 2, and similarly enforce not verified, enforce verified. And right now here it's a loop. So after if, we'll be giving else if, else if, two. And now here, as I've checked above for from. Now similarly, we'll be checking it for two. And here also will be, now here will be burning. So enforce not frozen from. Now we'll be giving else part. So else we will be doing the regular transfer of both from and to. So first we'll give from, enforce not, and similarly we give it to. So enforce not frozen to. Now we'll give enforce not frozen, sorry, enforce verified from and enforce verified. So we have completed our if else else. And now we'll be giving super dot underscore update from to and amount. So this will call the parent. This will call the parent update to perform actual event state challenges, state changes. Now they'll be declaring another function as enforce verified. So this is an internal function. It as the internal function. So for that, we'll be giving it here as internal view. And here in this if, we'll be saying that not registry dot, and here will be reverted to not verified account. Not, so this function is an internal function. You can see the internal function that is to enforce the allow list compliance. Now another function has enforce not frozen. Similarly, when we add this account, and we'll also have this as an internal function. So internal view, the registry dot is frozen in the account, then we'll just revert the frozen account. So that's it about the RWA token. So we have completed our contract of RWA token. So this complete contract is a compliance focused ERC20 token that is built on top of the OpenZeppelin library. So it is just integrating with the AllowListRegistry to enforce the verification and frozen checks on every transfer on the mint and burn operation. So this also have some additional features we have added like pausability for emergency shutdowns and then rule-based access control for minting, burning, pausing, and even the compliance overrides. And even we have post transfers by a compliance role to handle the exceptional cases. All right, that's the end of the part one. We have written the core RWA contracts, which form the foundation of our system. This setup ensures proper access control and tokenization logic before we move forward. So in the next part, we'll write the deployment script and the test files and then deploy everything to see it working in action.